So today we were going to see the very first topic of this gate mm, uh, the structures topic. Okay, stress and strain. Okay, now before moving to the stress and strain, you should know what are the basic classification of loads. Okay, you should know basic classification of loads. So if I have to say basic classification of loads, it can be classified in two different loads. Okay, so first one is a point load and the distributed load. Okay, so point load and distributed load. Now point load you can understand if we have a simple supported beam. Okay, simple supported beam, and I'm acting at some point is called as a point load. Okay, now the same point load is continuously distributed. The multiple amount of point loads are distributed equally, right, across the beam. We can say it is an uniformly distributed load, and if it is varying, the variation of this point loads varies from one point to another is called as a variable distributed load. Okay, so these are the basic loads. Now we will start with the what is stress. So you know stress defines by the force per unit area. Okay, so whenever I'm telling, please simultaneously note down the formulas also. Okay, so for stress is, now how the stress occurs, consider any beam. Okay, consider any beam. Let's consider cantilever beam. Okay, and I'm applying a load at the tip of this cantilever beam. Now what will happen, I am applying a force at some particular cross sectional area, right? So when I am applying a load, consider a point load at some cross sectional area, so what will happen, this particular beam will start to bend or start to deform, right, due to this particular load acting on it, right? So that when we are defining how much amount of force per unit area, that can be represented as stress. Okay, now what is strain? Now when this load is acting on this particular this beam, right, so this bend, due to this deformation, there will be some amount of changes in this cross section of this particular beam, right? So if I consider this is a length of the beam, due to the deformation, right, this is the original length, due to the deformation some amount of extension of length has occurred. So the strain defines the change in length by the original length, and some of the textbook they have defined as change in length as x. Some x amount of change has been taken by the original length. Now here the question is, when any beam, right, subjected to a load at some particular cross section, right, first it depends on its material, that how much amount of deformation that will take place. Okay, it depends on the how much deformation it will take place. Now this kind of question you can expect from the stress and strain. Let's consider you have two different material. One is aluminum, another is a steel. Okay, one is an aluminum, one is a steel. This particular aluminum has subjected a force F. Okay, here also F. They both have the same cross section. They both have the same cross section, that is A, right? Same length, same length, okay, same length. Here Young's modulus is 70 gigapascal. Here Young's modulus is 210 gigapascal. Okay. Now the question is, how the stress, the dependency of the stress will vary. That means how the stress of an aluminium and the stress of an steel will be connected. Whether it is 1/3 of this steel or the aluminium, how they are connected. How they are connected. Can you tell me how they are connected? You can unmute and say.
Ma'am, stress of steel is 3 times than stress of aluminium.
How you can say that?
Ma'am, modulus is stress by strain.
See, what is stress? Stress is load by cross-sectional area, right? So both the force, for an example, if I consider force is 10 kilonewton, okay, and the cross-section is 1 meter square. Here also 10 kilonewton, here also 1 meter square. Now the basic formula of stress is force per unit area, right? So 10 into 10 power 3 by 1. So what I will get? 10 kilopascal. Can I say that? So both the side I will get same. So can I say the stress for an aluminium is same as the stress for an steel? Can I say so?
Yes, ma'am.
Yes. So this one represents that if I want to consider the stress alone, which is independent of the material property. This is a very, very important point. Okay, this is a factor which is independent of the material property, because though the material property changes over here, I am getting the same factors, right? Other factors are same. If the force and cross-sectional area is same, then obviously this will also remain same. It is independent of whatever the material, right? Whether it is an aluminium, whether it is a steel, whether it is a composite material, right? So the same principle are being used in polariscope. I hope you have heard about polariscope. You know what is polariscope? Just let me know. Do you know what is polariscope? That is an instrument where using a light they analyze a stress concentration. They analyze a stress concentration of any material. Okay. Okay. All right. So this is one of the important point. Please note down. The stress is an independent of the material property. But whereas if I have to say for an strain, right, based on the different type of material, right, the elongation will vary, right? So how much when the load is applied, the amount of elongation, that will depends on the material property. So whereas the strain is dependent to a material property. All right, please make a note of it. Now sometimes the stress had been given as a unit of kgf per meter square or kgf per centimeter square, right? So these are the possible units. Okay, you should know how to convert the units. Okay, so you can note down this, how to convert the unit. 1 Newton per meter square equals to 10 power minus 4 Newton per centimeter square, okay, or 10 power minus 6 Newton per mm square. Okay. Please note down these notations, and it can be written vice versa. Then 1 Newton per mm square equals to 10 power 6 Newton per meter square, or I can say 10 power 6 Pascal. Okay. Now can I say 10 bar, because 10 power 5 Pascal represents 1 bar. Okay. So please note down these units. Okay. Right. Now strain. So there are of different type of strains are there. One is a tensile strain, volume strain, compressive strain, and the shear strain. So each one of them we will see one by one. Okay. So what is tensile strain? Tensile strain, it defines when there is some increase in length due to some external force, and the ratio of the increase in length to the original length. Okay, so as simple as that. Okay, so please note down. So compressive, so that means if there is any body something like this and it acting and tensile. I hope you know what is meant by tensile. Both the side you will be pulling outside. So due to this there will be some change in length, right? There will be some change in length. So it defines that change in length by the original length. Now compressive is just an opposite one. When there will be a compression load, so when there will be a compression load, so due to that there will be some decrease in length, right? So ratio of this decrease in length by the original length will give you the compressive stress. Okay. Next was a volumetric strain. By the name itself you can understand that you have to find out the change in volume. Okay, change in volume by the original volume of the body. Okay. Next comes shear strain. Shear strain is that when the amount of shear produced by the shear stress. Okay, maybe some one of the place is rigid, the structure will become something like that. Okay, to find the amount of angle, right? So likewise you can find out the shear strain. Okay, we will see the formula in the upcoming part also. Okay, so I hope you are noting down the points. Are you? Just let me know. Are you noting down the points?
Yes, ma'am.
Okay, that's good. Okay, now let's see what is tensile stress. Tensile stress is very simple. This is a beam, you can see this is a particular beam, right? So you are pulling from both the side, that is called as a tensile stress, right? Tensile stress can be defined as tensile load by the cross sectional area. Then tensile strain can be written as increase in length by original length. Okay, now comes compressive one. Compressive image. Oh, just a second. So you can see there is a compression is taking place over here, right? Compression. So what is the compression? Again the formula remains same. The it is getting pushed from both the end, so that resisting force by the area, and compressive strain is decrease in length by the original length. Okay. Now comes the shear stress. Shear stress is like induced, like there will be a motion in a two different directions, as you can see in this picture. So one in the right left hand side, another is in right hand side. So due to this, that particular object will start to shear, right? So this shear stress can be defined as the shear resistance per unit area. Shear resistance per unit area. Okay. So this can be defined as shear strain is as defined as phi, right? Phi is a transversal displacement by that means how much distance has been traveled from this point to this point by that distance, total distance traveled. Okay, by the total distance traveled. So this ratio will give you the shear strain. Okay. Now another one was missing, volumetric strain. Already I have discussed what was the volumetric strain. Okay. Now coming to a very important one is an elasticity and the elastic limit. Okay, elasticity and elastic limit. So already you know what is elasticity. Can you anybody define what is elasticity? What is elasticity? Anybody can define? Can anybody define what is elasticity? Anyone?
Ma'am, after the removal of external load, material return back to its original position.
Absolutely. So when any beam subject to a load, and after removing that load, right, it will come back to its original proper dimensional form. So that kind of thing is known as the your elasticity. One more point that I will be having, this is within the elastic limit. Okay. Now what happens, there is one law called Hooke's law. So it says that within the elastic limit, the stress will be proportional to the strain. Okay, that is very important. Within the elastic limit, the stress sigma is proportional to the strain, right? Once, that means if I have to draw a Hooke's law curve, right, I can say it will be a straight line. Now within this period, within this particular zone, whenever a load will be released, right, the particular body will regain its original size and shape. Okay, it won't deform. But after that, after this point, by increasing the load, right, increasing the load with some cross sectional area, the deformation which will take, right, which will be that the value which will exceeding the elastic limit, which will not have the property of elasticity, that will no longer belong to the property of elasticity, right? Did you get my point? So this is the zone of elasticity when I apply a load, and after removing the load my object will come back to this original formation. Once, if after I exceed this load, the further loading into the object, right, it will deform, right, but after I remove my load it won't be having a capability to come back to the original state. There will be some amount of deformation. It will not come back to the original one beyond this range of elasticity. Okay, noted? Right. Now how to define this Hooke's law? So I can, as I've said, which is within the elastic limit. So stress is directly proportional to strain. To remove this proportionality, they will be having some constant, so they write as this: sigma equals to E by epsilon. Okay, so what is sigma? F, that is a force applied by cross sectional area, equals to E. What is epsilon? Change in length by original length. So this can be also written likewise if I want to express in terms of force. So Young's modulus, change in length into A by L. Okay, or if I want to express E, so F into L by change in length into area. So you can write vice versa. Okay, now what is this? E called as a Young's modulus. Now you should know the some of the four standard values of Young's modulus. First of all, the Young's modulus for a mild steel. Okay, mild steel is, we generally consider 200 to 220, right? As a standard we take as near about 210 gigapascal. 210 gigapascal means 210 into 10 power 9 pascal or Newton per meter square. Okay, second one is an aluminium. It ranges from 60 to 80, but as an average we call as 70 gigapascal. Okay, again 70 gigapascal means 17 to 10 power 9. Then comes copper. Copper defines mostly 90 to 110, so we consider as 100 gigapascal. Then comes brass. Okay, brass ranges from 80 to 90, so as a standard we take as 85 gigapascal. All the units are in the form of gigapascal. This you must maybe some of the problem they may not give you the value of Young's modulus. In that case you have to consider this basic values of this Young's modulus, okay, to solve the well defined problem, right? Now this is goes the Young's modulus. Then next we have the modulus of rigidity. This modulus of rigidity says that it's the ratio between the shear stress to the shear strain. Okay, it is a ratio between the shear stress to the shear strain, denoted by either the letter C, N or G. Okay, C, N or G. Another is a bulk or the volume modulus of elasticity, which is not written over here. Another one is a bulk or volume modulus of elasticity. Okay, So this can be defined as a letter called K. Okay, the bulk volume modulus of elasticity. It's a ratio between the normal stress to the volumetric strain. Okay, it's a normal stress to an volumetric strain. Let's consider epsilon suffix v or volume. Okay, it represents as the letter K. Right. Next, we have factor of safety. This is very important. They might give you the value. It is some kind of problems you can expect based on factor of safety. Now this factor of safety you may need to apply across this entire structures. Okay, this is a very important part. So you should know what is factor of safety. The factor of safety defines that it's a ratio of the ultimate tensile stress to the working permissible stress. Okay, ultimate stress to the permissible stress, or sometimes we call as a yield stress, permissible or the yield stress. Okay, this defines the factor of safety. Okay, now from here you can understand what will be the value of factor of safety, whether it will be less than 1 or always greater than 1. Can you tell me that? Whether it will be less than 1 or it will be greater than 1. Sorry dear?
Less than 1.
No, see the factor, the ultimate stress is more, always ultimate will be the highest one compared with the permissible one. Okay, so in the numerator we will be having more value compared with the denominator. So obviously always you will have some value should be greater than 1. Okay, always you will have some value greater than 1, factor of safety. Right? Clear?
Yes, ma'am.
Now we will see that how this material property changes with different kind of materials and what are the typical graphical representation of it. Okay, so you can move to the beginning. Just a second. Now you have a very important topic, that how the stress strain acts. Okay. Just a second. Fine. Okay. So this is, we have the stress, here we have the strain. Okay, now from this point 0 I'm stretching, change the color to okay. Right, so here we have some of the significant points. Okay, the first point is here, which explains this is the proportional limit. Okay, proportional limit. This is the upper yield point, this is the lower yield point, or I can say permissible point. Okay, at this particular point, if I want to represent, is a amount of permissible stress. Okay, this is the actually the permissible stress, and along with this point is an permissible strain. As we increase the deformation, it reaches an ultimate, the most peakest is called as an ultimate point. Okay, this is the ultimate. This is an ultimate point, and after reaching the ultimate point, as we keep on give the loading, it will leads to an fracture, and so it is called as a fracture point, or it is called as a breaking point. Fracture point and the breaking point. Is that clear with all these points? So these are the basic points. Now if I have to see the range between this zone to this zone, is called as elastic zone. Elastic zone is nothing when you apply a load into this particular cross section or a body, and you remove the load, it will come back to its original position. That represents the elastic zone. Here to here defines a plastic zone. That means it will no longer come back to its position. Now from the ultimate point till the yield point defines a strain hardening. That means after the plastic zone, right? So here what happens in plastic zone, once you remove the load, it will come back, but it won't come back to the original state, right? But after this plastic zone, if you keep on give the apply the load, right, it will increase its deformation, and it will increase its stress, right? That particular, and it will not come back to this original deformation ever again. Okay, then after the strain hardening, from the ultimate point to the fracture point, we defines it's a failure zone or necking. Okay, failure zone, or it is known as a necking, right? Now you can also expect one kind of problem, or you can some kind relevant to that. So they can give you the value of change in strain and change in stress, and from there they will ask you to find out the Young's modulus. How will you find, right? They will give you some points of stress and some values of strain, and from there you need to find out some values of Young's modulus. How will you find? Any idea? How will you find Young's modulus? Any idea?
Ma'am, dividing the change in stress by change in strain.
Very good. So you have to divide the, ultimately you have nothing but you have to find out the slope. The slope of this curve will represent the Young's modulus, right? Slope of this curve will represent the Young's modulus. And remember, if they ask the yield stress, so this will be the value of the yield stress. Okay, so from this point to this point, yield stress, and they can, instead of giving the value, they can give you the graphical representation. Okay, so you should able to find out the points. This is the yield strength and this is the ultimate strength, right? So what is the factor of safety? Factor of safety is ultimate strength by the yield strength, right? Okay, now one more question, maybe even in upcoming also we will see, but since we are looking for this particular graphical representation, so that kind of questions can also be expected to find out the modulus of resilience. What is modulus of resilience is that it shows that how much amount of elastic energy has been absorbed by the material. Okay, that is mean by the modulus of resilience. Modulus of resilience, it shows us how much amount of the maximum amount of energy has been absorbed by this material. So this can be found using half sigma E. Okay, that this is a formula, that is half sigma E. To find out this parameter, you should find out the area under this particular graph, the shaded portion which I am doing, elastic zone. So you should find out the area under this elastic zone. Clear? Noted? Just let me know.
Yes, sir.
Okay, next, similar to that, they can also ask, find out the resilience. So in competitive exam they ask such kind of question. Okay, so they will give you the graph and they will ask you find out this particular thing. So using this area under the particular thing you have to find. So resilience of material can also be expected. Resilience of material can be found by the product of modulus of resilience into the volume of the material. Okay, by the volume of the material. So volume of the material will be given, the modulus of resilience can be found from this area under this curve, right? Substitute the value, right? Substitute the value, you will get the answer. Done? Shall I move to next?
Yes, ma'am.
Okay. Next is, so let me open the paint. Can you see my screen right now?
Yes, ma'am.
Okay, right. Next, another one is there. You have to know how this stress and strain depends in different type of material. Okay, how this stress and strain depends on different type of material. So first of all, I will draw for an, this is a usual one for an any ductile material. Okay, when we have any kind of material. Okay, next, where we'll have all the points, where we have the proportional limit, where we have the ultimate points, yield points, we have the ultimate points and the fracture points. So that will defines the ductile material. Next material which will have a little bend and then it will move, but not necking over here is not that much but slightly. Such kind of material have the soft ductile material. Soft ductile material. Okay, next we'll have the just a straight line, then the fracture point. So this one defines as a brittle material, right? Brittle material. Brittle material, I hope you know what does it mean, that easily it can break. Okay, easily which it can make. Next we have the plastic material. Plastic material, first it will go and there won't be any curve and they'll be having a smooth curve, and after gradually at some point we'll be having a straight line. Okay, after some point we'll have a straight line. So that will defines a plastic material. Okay, next one we will have a elastic material, when like rubber. Okay, it will something like this, opposite curve, so it will be the elastic material. Okay, so ductile material here means you can say mild steel, soft material like aluminum, copper, then brittle means I can say glass, plastic, you know, plastic material, elastic means rubber, right? Have you noted down? Okay, now in comparison to this we can draw one more graph to see the characteristic of the different types of material, stress, and here is a strain. Okay, I will draw 4 different graphs. Okay, one graph which is go at a very peak and steeply fall. Okay, one is just a straight line and break, one which have its curve and then break, and one which is slightly go like this. Okay, four different graph. So the first one characterize when we have a steep and then it starts to fall, it has a characteristics of the strongest and the stiffest. Okay, this has a characteristic of the strongest and the stiffest. Next, which will increase and then leads to break, it is having the brittle in nature. Okay, which has a curve, then ups and downs, which is the most ductile in nature, and which doesn't have any curves and bends and go along with that increase in as we increase the load and they leads to an increase in strain. That material represents the most softest ductile material. Okay, noted. Just let me know once you have noted down these things.
Yes, ma'am.
Okay, right. So there are another four different plastic and elastic materials you should know. One is the linear elastic, then linear elastic perfectly plastic, then we have linear elastic hardening plastic, then we have linear elastic hardening plastic with unloading. Okay, we have four different types and we will see how the stress and strain deforms for each and every factor. So for the first one, when the linear comes into the picture, so it will be something like this, and strain, which is the name itself, it shows linear, right? It will be a straight line which is proportional line. Okay, sigma will be proportional with the strain. Then when we talk about linear elastic and perfectly plastic, okay, so it will be something like you should know the graphical forms, right? Okay, when it is perfectly plastic, it will be horizontal. Okay, now when it is just an hardening plastic, it will change its nature slightly. It will increase because it's a linear elastic. Then from the horizon it will just have something like this. Okay, that means it is inclining upwards, it's increasing. But in case of elastic hardening plastic with unloading, it will be causing a looping system, a looping formation. Okay, it will cause something like looping formation. Right? Please let me know, have you noted down?
Yes, ma'am.
Okay. Next, another important stress strain curve for an consistent of carbon content. Okay, carbon content. Based on the percentage of carbon content in a material, so how this stress and strain will correlate. So this is strain, this is stress. We have three different types. When the carbon content is high, equivalent to 0.6 to 2.5 percentage. Okay. This is a medium where it consists of 0.3 to 0.6 percentage, and low okay. So what this graphical form says, what does it speak? That means when the carbon content is low, there is a low value, right? When we have the low carbon value, what happens? What happens as compared with the high?
Hardening.
Hardening is occurring, but we can say that it will leads to fail at a very low stress level. Okay, it cannot resist much amount of stress level. So more the carbon content, it can attain larger amount of stress level, right? Okay, so see, this is the for the high stress, this is for the low stress, right? Am I right? You got my point? So the high amount of carbon content can lead to a larger amount of stress form as compared with a low concentration. Clear? Just let me know. Right? Shall I skip to next?
Wait, ma'am, I'm noting down.
Okay. Just note it down. These are the small facts that you have to remember. Even in future when you're doing research or anything, it will be very much useful.
Yeah, ma'am, I'm finished.
Okay. Now there are of two-dimensional systems. Okay, so the strain can be defined in another two ways. One is a longitudinal strain, another is a lateral strain. Okay, so longitudinal strain, I have already said that change in length by the original length. Okay, change in length by the original length. Now there is also called as a lateral strain. That means when any object, okay, suppose, see this, look into this figure. This is a real this was the original, sorry, just give me a second. So this is the original bar, okay, original beam of length is L. Now it has been pulling from both the end, it is forming a tensile stress. Okay, so when it is containing a tensile stress, both the side there will be some amount of elongation. Okay, there was some elongation. So when it's elongating, so in the this length, across this length, okay, suppose consider it's a D, right, original diameter or the depth is D, right. So when it's pulling, there will be some decrease in depth, right. You can see in this figure that shows. Now that along the other end, okay, lateral end, when we want to see the change in from the original dimensions, that one represents the lateral strain. That says a change in depth by the original depth, or if it is in circular, we can say change in diameter by the original diameter. Okay, you got the difference between longitudinal strain and lateral strain. So lateral strain is change in length by original length, and that was the longitudinal one. Lateral means change in depth by the original depth or diameter. If it is a circular rod, you can consider as a diameter. Right, now we will see one more important term called as a Poisson ratio. Okay, let's see what is Poisson ratio. Poisson ratio defines the lateral strain by the longitudinal strain. Lateral strain by the longitudinal strain. Okay, so what is lateral? Already I have said, change in diameter by original diameter or the depth by the change in length by the original length. So here, however means you define, it doesn't matter or much of it. Okay, that later that you mentioned. Again, here you need to remember few of the Poisson ratio values. Okay, few of the Poisson ratio values. So first of all, for the mild steel, okay, for the mild steel, the Poisson ratio values is 0.288. okay, 0.288. Then for aluminium it is 0.330. okay, then for copper it is 0.355. okay, then for brass it is 0.340, and for cast iron it is 0.270. okay, so the Poisson ratio says that it is a ratio between the lateral strain by longitudinal strain. Done? Shall we move to the next? Just let me know once you're done.
Mine is done, ma'am.
Okay. Now, okay. Now next, very important. Okay, this is the if you are getting like any question where they are defining like this kind of thing, okay, relation, how the relationship between the stress and strain. Okay, so they are telling that there is an object, okay, a bar. So in the x direction, this is x direction, this is a y direction. Okay, negative y, positive y. Okay, in the positive, in the x direction, you are having a normal stress called sigma 1, and in the y direction you have a normal stress as an sigma 2. Okay, in this condition, how will you calculate the total strain? Okay, how will you calculate the strain acting on this particular cross section? Okay, so in that regards, if it is a two-dimensional, if they have given only the two direction, that is x and y, so you have to use this formula for when you are finding the stress. Okay, when you're finding the strain along the x direction, what you have to do is sigma 1 by E minus mu is an Poisson's ratio of sigma 2 by E. E is the Young's modulus. Sigma 1 is along the x direction, sigma 2 along the stress along the y direction. To find the strain at the other direction, the formula will be sigma 2 by Young's modulus minus mu sigma 1 minus E. Right? Got it? This is a very important one. Sometimes they will give you the schematic diagram, they will give you the values, and they will find out the strain in one of the direction. Like they will give precisely which direction they are asking to find out the strain. Okay, so note down this figure and write down this formula. If the sigma 1 is equal to sigma 2, if sigma 1 is equal to sigma 2, then what will happen? And the material is same material, then what will be happening with the sigma 1 and epsilon 1 and epsilon 2? What will be the formula for epsilon 1 and epsilon 2?
Sigma by E into 1 minus U.
So can I say epsilon 1 will be also equals to epsilon 2? Because if sigma 1 equals to sigma 2, right? So everywhere let's consider sigma itself, right? So what is epsilon 1? Will be sigma by E minus mu sigma by E. Here epsilon 2 will be sigma by E minus mu sigma by E, right? So both are same. So can I state that sigma epsilon 1 will be equals to epsilon 2? Can I state?
Yes, ma'am.
Yes. So they will ask such kind of question. Okay, so they will define this problem and they will say that sigma 1 acting this way, sigma 1 is this much, and you need to find out how they are varying with each other. Okay, So you have to be alert about this thing. Now this is for the two directional, as I've said, when it is x and y. Now what will happen in the z direction? Suppose if happens something like in this figure. You can see in this figure we have in three different directions. One is x, y and z direction. So along the x you have sigma 1, along the y you have sigma 2, and the z direction you have the sigma 3. Okay, similar kind of thing. So when you are considering sigma 1, epsilon 1, so sigma 1 by e, and others will be in negative zone. Thus consider mu outside, sigma 2 by e plus sigma 3 by e. Okay, when you are considering sigma 2 by e minus mu sigma 1 minus e plus sigma 2. Then when you are finding epsilon 3, sigma 3 by e minus mu sigma 1 plus e by e plus sigma, here it will be 3, right, 2 by e. Fine. Noted, right? Have you noted the formula?
Yeah.
Yes, ma'am.
Okay, fine. Okay. Next we have analysis of bars and section. So before coming for the analysis and bar and section, I would like to note down one more thing. Write down the relation between the moduli. Relation between the moduli. I hope you can see my screen. Okay, so that means we are going to see the relation between E, G and K. What is E? E is the Young's modulus, G is the rigidity modulus, and K is a bulk modulus. Okay, so we have three formulas that how they are connected with each other. Okay, first formula is okay. Okay, so what is mu? Mu is the Poisson ratio. Okay, G is the rigidity modulus, K is the bulk modulus. So you can expect a problem combining this relation between the elastic moduli. Okay, these are the very important formula So I used to use one tricks to remember this particular formula. Okay, how? See the kg, right? So I used to remember 9 kg. Now I'm going to split this 9 kg, right? So square of this root over this 9, okay, is 3 k, and I'm going to split plus g, right? Just remember kg itself, so it will be easy. So do not put the g first and the k afterwards. Okay, so that will help to keep like to remember, right? So sometimes you need to use some tricks, that since E equals to 2g 1 plus mu and E equals to 3k 1 minus 2 mu, so you need to use in a formula, like you can say 2g 1 plus mu equals to 3k 1 minus 2 mu. I can also write in this way, right? So you can simplify and you can solve, find out the unknown parameters. There are some problems which you need to use this concept. Okay. Right. Is that clear? Noted? Shall we move to the next? Just let me know.
Sure, ma'am.
Okay. See, here we have lot of many of formulas, so you have to be very careful and you have to read the question and understand which kind of problems will be applicable on this particular thing. Okay, right. Now next comes the analysis of bars of various sections. Okay, so we will have various sections, and as I've said, which will be in series and parallel. So first we are seeing in series, when the different kind of bars are connected with each other. Okay, and each bar consists of different length and maybe of different depth or different cross-sectional area. Okay, and but when these bars are subjected to an same axial load called as P, right? They have the same axial load, and they are considering that all the bars are in same material, okay, different length and cross section, but of same material. So such kind of thing can be to find out what they will ask to find. They will ask you to find out the complete total change in length. Okay, complete change in length. To find out the complete change in length, this is the formula. Okay, this is the formula. So where P is the axial force, okay, there is a change in length. Suppose there is a change in material also, so this will be the E1, right, corresponding for the section 1, what is the corresponding length, what is the corresponding cross section area, and what is the corresponding material. Okay, simultaneously for the section 2, section 3, and if you have in additional sections, you have to keep on add on the factors, that L4 by L4 into A4, plus if you have another section, L5 by E5 by A5, right, so on, right? Got that point? So this is for the bars of varying section. Okay, let's look into one of the problem. let's solve this problem. Okay, first problem, you can see an axial pull of 35000 Newton is acting on a bar consisting of 3 lengths as shown in figure. If the Young's modulus is 2.1 into 10 power 5 Newton per mm square, determine the stresses in each section and the total extension of bar. Okay, so they have given you the formula and they have given you the figure, right? In this given figure they have given the p value, right? So they have given the diameter, right? They have given the diameter, so from there you can find out the area of the section 1, the area of section 2, and they have given the area of section 3. Length is given, L1 is given, L2 is given, L3 is given, P is given, E is given. Here E is common, right? So you can use this formula. So you can use this simple formula to find out the total extension of bar. Okay, and to find out the stresses in each section, how you are going to find? Suppose for sigma 1, right? For sigma, what is the sigma? Force per unit area. So when you are finding for the section 1, so you will use force is constant, so you are going to use A1. Sigma 1 equals to P by A1. For sigma 2, P by A2. Sigma 3 is P by A3. Okay. Now you find out the answer and tell me. Solve and tell me. First you tell me what is the total extension of bar. First you solve, calculate and tell me the answer. Tell me the answer. You can tell me the answer. Okay, you got the answer over here. Right. So let's check the answer. Okay. So total extension is coming about 0.183 meter. Sorry, mm. Are you getting the same answer? Just let me know.
0.1837.
Okay. 1837. And what about the individual one? Have you got it? These values? Just check it. Sigma 1, sigma 2 and sigma 3. Okay. Just let me know. You can unmute and tell me. Okay, shall I move to next? I'm waiting for your response.
Yeah, ma'am, we got the values.
Okay, okay, fine. Next, we have another different kind of problems. Okay, right? Now, this is called as a principle of superimposition. Now, just look into this particular problem. Okay, so here it says that a brass bar having a cross sectional area, the cross sectional area is same across the thing, and but their axial force are varying. Okay, the cross sectional area is going to be same here, and the material is also same, but they are having a different kind of axial force in different locations. You can see we have 3 sections over here. Okay, here is a section 1, section 2 and section 3. So what the amount of pulling at the A point and the surface D point is different. So in that case, what you have to do is we need to find out the the summation of forces. Okay, we need to find out the summation of forces, right? To find out the summation of force, the amount of force will be here, right? How we can find? First we need to consider 80, because we know tensile direction is positive. These are the compressive direction. Okay, compressive direction, okay, that is minus 20. Another is the tensile direction is plus 10, right? Now we need to again split down the section, that how much amount of force will be acting on this particular cross section. So when you are considering the first section, we have around 50 kilonewton in the tensile direction. So this is section 1. Okay, section 1. So we need to create a same load on both the side, right? We need to keep the P1 same. So if here we have our 80. Now if I cancel out 50, then how much will be remaining? 30. Now let's consider the second element. We have the 30 remaining. Okay, 30 amount kilonewton is pending. Now next we have our 20 kilonewton. It is in compressive in nature. So if I add on 20 over here, right, what is the remaining? 10. That will also in a compressive in nature. Next one, when the third section we will see. So what you have to take? We have to take a negative both the compression directions. Both we need to take in an compression directions. Okay, so likewise you have to frame this you need to split this bar. Okay, did you get the point? how you need to split this bar, and after splitting this bar you have to form the same way to find out the elongation. How? So once individually you are going to find out the change in length. So for what is the change in length for first one? So you know what is the change in length? Del L equals to, from the Hooke's law, P1 L1 by AE. This is the formula, right? Area is same, E is same, P is different, right? L is different. So using that you are going to find the change in length for the section AB, then section BC, then section CD. Then you are going to sum up all the facts. Okay? Did you get this point? Just let me know.
Yeah, ma'am.
Huh?
Yes, ma'am, got the point.
Okay. Now you see, look into this problem. A is given, E is given, L is given, right? They have split it. You have found out the change in length. Here you see in the BC, we have the decrease in length. Why? Because it is in compressive nature. So it will be in decrease in length, right? You have to consider that. That means negative. Again, here what we have? Compressive, right? When you are forming the CD, it is also compressive. It is in decrease in length. So to find out the total bar, right? So this is del L1, del L2, del L3. So when you are adding, it should give us minus, because it is decrease in nature. And whatever you will get, that will be the value. So you have to keep that in mind. Based on this, how you are splitting this particular cross section, whether it is a compressive or tensile, likewise you will get your total elongation. That means it is decreasing in length, means it is overall it is getting compressed, right? Overall it is getting compressed. So they can ask you the statement like, after changing on this, what will be the nature of the particular component of this bar, whether it will be tensile in nature, first increase then decrease, right? So you should be able to calculate, and you can find out the what that it represents. Okay, whether it's a decreasing or increasing. Noted? Okay. Next we will have they ask us small problems based on this analysis of uniformly tapered circular rod. Okay. So there is some taper circular rod. So this particular point is a D1, another is getting D2. Total length is L. Both the side we have a tensile load, that is a P. They have shown. The final expression only you need to remember. Okay, for an this is this one. Okay, you need to remember the final expression, no need to remember the derivation. Okay, so if they are asking, they are giving like find out the elongation for an taper circular rod, you should able to find out. So P is a load, tensile load, L is a length, E is a Young's modulus, and D is a diameter. Okay, how to find the diameter? Right, to find out D1 minus D2. Okay, right, D1 minus D2 will give you the D. So note down what is D, D1 minus D2. Okay, sorry, D1 it will be not minus, equals to D2. D1, if D1 is equal to D2, you'll have this formula. If D1 and D2 is different, you will have 4 PL by pi E D1 into D2. Okay, this will be the formula. So there is some typo error might be. D1 equals to D2, right? Did you note it? This is for an uniformly tapered circular rod. This is for the circular rod. Shall I move to the next? Just let me know. You can unmute and tell me.
Yes, ma'am.
Okay. Next we have this uniformly tapered rectangular bar. Okay, this is an uniformly tapering rectangular bar. The previous one was a circular rod and this is a rectangular. Okay, so for this is the formula. This is the formula. Okay, so first note down PL by ET A minus B log power E log E A by B. Now what is A and B? A means is a width is bigger, where the width is bigger end, right? Note down what is A and B, where the width is in the bigger end. B represents width at the smaller end. T is a thickness of bar. T is the thickness of the bar. Okay, so that is very important to define what is A and B. A is the width at bigger end, B is a width at the smaller end, and T is a thickness. Okay, okay. Shall I skip? Shall I move to the next? Just let me know.
Yes, ma'am.
Okay. Okay. Now coming to another very important analysis of bar of composite section. Here composite section says that they will be having a single bar, they will have a single like a fixed zone, single fixed zone, and from the fixed zone we have a different materials will be compiled together and a single amount of load will be acting on it. So what kind of phenomena will occur? Okay, so here we have 1 and 2, right, of an different material, and the load is acting and the length of this particular thing is same, and here the load acting on that is this P is a total load of an composite bar. Okay, composite bar in the sense like combination of one or more bar, but though their length is remaining same of a different bar. The cross sectional area is different for an bar 1 and bar 2, can be defined as A1 and A2. The Young's modulus and for 1 and 2 is different because they are different material. Okay, and the load acting or the load shared, that means P is the total load, so shared means then I can say P1 plus P2 is the total load. So P1 is a load shared by the bar 1 and P2 is a load shared by the bar 2. Then if the load is different, then obviously the stress induced will be also be different on both the different section, right? So in this kind of particular composite section, what we can say that P1, the total load, okay, or the force acting on this composite bar can be written as the combination of this bar 1, the load acting on the bar 1 and load acting on the bar 2. Okay, now coming to the stress acting on the bar 1 and 2. Okay, stress is sigma equals to P1 by P by A, or force per unit cross sectional area. So we can define for the bar 1, that is stress induced in the bar 1 is P1 P1 by A1, and stress induced in this section 2 or the bar 2 is P2 by A2. Now we got this formula, we have this. Now from here, sigma 1 equals to P1 by A1, we can write that P1 equals to sigma 1 by A1, simply exchanging the values. Similarly, sigma 2 equals to P2 by A2, we can write P2 equals to sigma 2 into A2. Now we have this value, substituting these values over here, right? So what we'll get? We'll get this P equals to sigma 1 A1 plus sigma 2 A2. Now coming to the strain, since both the bars are connected, see here both the bars are connected in an same fixed zone, and there is some kind of plate where altogether it is acting at some point, right? And the length of the bar is same. So due to that, what the strain says, a strain for the bar 1 will be sigma 1 by E1, strain for the bar 2 will be sigma 2 by E2, right? So in this case, since they are attached in the same fixed zone and they are pulling in the same form and the length is same, so what we can say, the strain in the bar 1 will be the strain in a bar 2. Okay, so if the strain in a bar 1 and same in the bar 2, then we can define like this. Okay, so these are the conditions. Okay,
Ma'am, how can it be equal, ma'am? Strain in 1 and strain in 2, because the stresses are different. And
see,
then only
okay, since the end of two bars are rigidly connected, okay, they are rigidly connected, that means here they have some kind of plate, they are connected, overall they are applying the load. Okay, so due to that, each bar will change in length by the same amount. Okay, also the length of each bar is same, so hence the the ratio of change in length to the original length will be same for each bar. Okay, because since it is rigidly connected, we will see when it is not rigidly connected how it happens. Okay, that also we will see, but here when it is rigidly connected, so this is the form. That time the strain will be equal to the strain of bar 1 will be same as a strain in bar 2. Okay, since the main point is they are rigidly connected and the load is applied. Okay, fine, just let me know.
Okay, ma'am.
Okay, so till here we have just completed, okay, the bars of a composite section. So what I will request, already I have shared this textbook with all of you, so please do go and refer this textbook. This is the strength of material by Rajput. Okay, sorry, this is an R.K. Bansal. This is a R.K. Bansal book. Okay, so if you have a Rajput, you can also refer to the Rajput also. Okay, so this books already I have shared with you, right? So please go through and look into the problems, solve it, because I feel like taking like this will be much convenient, because there are lot many things in this particular thing. Okay, if I make PPT, it will be much difficult, right? So I can take directly over here. Okay, the things which is missing in this textbook, that also I have also discussed. Okay, like stress and strain curve, that also I have discussed with you, right? Okay, so today evening you will have a flight mechanics class. Okay, and again tomorrow we will have a structure class. Okay, Sunday again we'll have the structure class. All right, so we will proceed fastly, right? So shall we wind up the session over here?
Yeah.
Okay, ma'am.
Okay.